One of the operations you might want to do in three-dimensional space is a reflection. And what we're going to do in this video is try to understand reflections through 2 points of view. First, through the point of view of vector analysis, which is what most of you guys are probably familiar with, which includes dot products and cross products. And secondly, through the point of view of quaternions, where we're going to derive a quite compact formula for doing a reflection. To better understand reflections in general, let's first work in 2 dimensions. What I have here is a mirror, which I'm going to draw in by this line here, called M. And associated to that mirror, I have a normal vector called n hat. And remember what the normal vector is. That's a vector which is perpendicular to the plane, or in this case a line because we're working in 2 dimensions. And I have my vector of interest v. And what I want to do is I want to take this vector v and reflect it through the mirror. Now our intuitions are going to tell us that the vector should land somewhere over there, but let's be more precise with this. And to be more precise, what I'm going to do is take this vector v and decompose it into 2 parts. The first part is going to be a projected vector in the same direction as n. And I'm going to call this first newly derived vector v parallel, because it's parallel to n. So that's the first part. And the second part is going to be a second vector which is perpendicular to n. And you can see how easily I obtained it right there. I just used that projected line, I drew in a vector there. And this vector is going to be called v perp, because it's perpendicular to n. And of course, I can always take this vector here, and instead of drawing it right there, I could project this onto the mirror, the vector onto the mirror, and just draw in v perp right there. So what have we done here? We've taken the vector v, and we've decomposed it into a v parallel, right there, and a v perp. And hopefully you can see that the vector sum of v parallel and v perp is indeed the original vector v. So this is what I've done symbolically. V is equal to v parallel plus v perp. Of course, what I'm interested in doing is taking that vector v and reflecting it through the mirror. And I'm going to call the newly reflected vector v, the thing I want, v prime. And I claim that v prime is going to be equal to v parallel prime, which is a reflected version of v parallel, plus v perp prime. And what I'm assuming here is that reflections are linear operators, which they are indeed linear operators. I just haven't proved that yet. But let's go right ahead with this. So I have v parallel, and I reflect v parallel through the mirror. So that's going to look something like this. But remember, v parallel has a special property that is 90 degrees to the mirror, which means once that gets reflected through the mirror, this v parallel prime is really just the negative of v parallel. So v parallel prime is equal to minus v parallel. So that's the first operation that we've done. Now we just have to find what v perp prime is going to be. Now, since v perp is right on that mirror, when you take a vector on the mirror and try to reflect it, it's just equal to itself. So v perp prime is just equal to plain old v perp. So these are really the key observations to make when we're doing reflections, that when we take the component of the vector which is perpendicular to the plane and we send it through the plane, we reflect it through, that just adds a minus sign to that. Whereas when we take the component of the vector which is parallel to that plane, that's unchanged upon reflection. So now that we have the 2 new vectors, minus v parallel and v perp, we're going to just take the vector sum. We're just going to add those 2 vectors together, which is going to generate this vector here. And this vector is the one we're looking for, which is v prime. And hopefully this agrees with your intuition, that if we had this vector here, when we reflect it through the mirror, it should land approximately there. What I'm going to do now is work with this formula a little bit. And what I'm going to do is I'm going to return to this first formula, that v is equal to v parallel plus v perp, and I'm going to solve for v perp. And after doing a little rearrangement, v perp is going to be equal to v minus v parallel, just moving that to the opposite side. And what I'm going to do is I'm going to take this new expression for v perp and insert it right there. So what I find is that v prime is equal to minus v parallel plus what I have here, which is v minus v parallel. And I notice I have two copies of v parallel. So this can be rearranged as v prime is equal to v minus 2 times v parallel. So that's a pretty nice formula so far, and you should convince yourself that this formula actually works geometrically. But let's now work with this formula a little bit more. So there's my formula and a little picture of what's going on here. The last thing we're going to do is make a substitution for this v parallel. Now remember, v parallel was just the projected vector onto n, and it was in the same direction as n. So what that means is that v parallel is some scalar multiple of n hat. And if I choose this vector n hat to have length of 1, it turns out that this scalar factor is going to be the dot product between v and n hat. So that's the projection formula if you haven't seen that before. If you haven't seen that before, I recommend you learn a bit about it. But once I have this formula, I can just substitute that in right there. So what I have is that v prime is equal to v minus 2 times the dot product between v and n times n. And that's the final formula, the final reflection formula for vector analysis. Hopefully you can see here that at least in 2 dimensions, if I give you some mirror M, which has an associated unit normal vector called n hat, if I give you some input vector v, you can just use this formula on the right hand side here to calculate the reflected version of v called v prime. So we've tackled the case for 2 dimensions, but I claim that 90% of the work is already done because the case for 3 dimensions is more or less the same thing. So instead of a mirror, I have some plane here, and again, associated to the plane, I have this normal vector, which is perpendicular to the plane, and again, I'm going to choose this vector to be of length 1. So n hat is going to have length 1. And then I have my vector of interest. Now this vector is going to live in 3 dimensions, called v. And I play the same game. I take this vector v, I break it into 2 parts. The first part being the projected vector onto the normal vector n hat. Again, I call that v parallel. And then I look at the v perp vector. And again, I take that vector and I can slide it right down onto that plane there. That's also v perp. And then I take v parallel and v perp, and I think about what happens when you reflect them through the plane. And again, when I take this vector, reflect it through the plane, that's just the negation of v parallel. And then this vector v perp is unchanged when reflecting through the plane. So I take the sum of this vector, negative v parallel, and v perp, and the vector sum is going to look something like that. And this is going to be the reflected version of v. And hopefully you can see intuitively that makes sense. If I take some vector there and I reflect it through that plane, it should land somewhere down there. And you can play the same game and you're going to get the same exact formula. Now before moving on to the quaternions, let me give you a numerical example how to reflect using this formula. What I'm going to do is I'm going to consider the vector v, which is going to be 1, 1, 1. So the vector is going to look something like this: 1 in the x, 1 in the y, and then we go up 1 in the z. So the vector is going to look something like that. There's v. And what I'm going to do is I'm going to reflect that vector in the xy plane. So I'm going to reflect it through this plane here. And now we have to determine what the normal vector, the unit normal vector n hat, is going to be. And it turns out, hopefully you can see that if I have this xy plane here, the unit normal that sticks right out of it perpendicular is going to be the vector 0, 0, 1, which is going to look something like that. That's n hat. And now what I do is I just apply this formula. So I have that v prime is equal to 1, 1, 1 minus 2 times the dot product. Now let's calculate the dot product there. I have 1 times 0 plus 1 times 0 plus 1. So the dot product is just 1 times n hat, which is just a vector 0, 0, 1. I have 1, 1, 1 minus 2 times that vector, which is 0, 0, 2. And I just subtract component-wise, and I get 1, 1, then I have 1 minus 2, which is minus 1. So this formula is telling me that v prime is 1, 1 minus 1, which makes sense because the x and y components are the same, whereas the z component just got a minus sign. So that vector is going to go, instead of up 1 in the z direction, it's going to go down 1 in the z direction. So it's going to land somewhere down there. You might notice too that instead of picking that unit normal vector to be 0, 0, 1, if we had instead chosen n hat to be 0, 0, minus 1, which is a perfectly good choice of a unit normal vector, it wouldn't have mattered because this n here will give a minus sign when taking the dot product with v, and this n hat here will give another minus sign. So those two minus signs will actually cancel, which means that it doesn't actually matter which of these two choices of unit normal vector you choose. So this is the reflection formula I get for vector analysis, and now I'd like to turn our attention to quaternions. Now, if you aren't familiar with quaternions, I recommend you check out some of my other videos on the introduction to quaternions and also the video about the dot products and cross products, because you're going to better understand how to multiply quaternions in that video. So what I'm going to do is I'm going to try to write this vector equation in terms of quaternions. And what I'm going to do is I'm going to define up a few quaternions. The first one is going to be the quaternion n, which is going to have 0 in the scalar part and n hat in the vector part. Because remember, one way of thinking of quaternions is a scalar part plus a vector part. So there's my first quaternion n, and I'm going to define up v in a very similar way. It's going to have 0 in the scalar part and v in the vector part. And finally, v prime, which is also going to have 0 in the scalar part and v prime in the vector part. Now what I'm going to do is I'm going to just experiment around. I'm going to multiply n times v. Just do quaternion multiplication. And what's the new scalar part going to be? I'm going to have 0 times 0, which is 0, minus the dot product of n hat with v. So what I have in the new scalar part is minus n hat dot v. Now in the new vector part, I'm going to have 0 times v plus 0 times n. So I have 0 so far. And then finally I have plus the cross product of n hat with v. So the new vector part is going to be n hat cross v. Now if you play the same sort of game and instead of multiplying n times v, you multiply v times n, what you're just doing here is you're just swapping out the v's and n's. So my formula is going to be, in this case, minus v dot n hat in the scalar part, and in the vector part it's going to be the reversed version, which is v cross n hat. And now what we're going to do is we're going to observe that the dot product is commutative, so minus v dot n is actually the same thing as minus n hat dot v. And we're going to notice that the cross product is anti-commutative, which means if I want to flip the order around, I've got to put a minus sign in. So v cross n hat is equal to minus n hat cross v. And that's still equal to vn. So what do we notice here? That when comparing nv and vn, the scalar parts are the same, whereas the vector parts are opposites. For my next trick, what I'm going to do is I'm going to take that quaternion nv and add it to vn. So I have nv plus vn. So I'm just going to combine those scalar parts together and combine the vector parts together. Since those scalar parts were the same, what I get is minus 2 copies of n dot v. And those scalar parts, being opposites, they just cancel each other out. So the vector part goes to 0. So now we observe that this new quaternion, nv plus vn, is all scalar part and no vector part. And what I'm going to do, just for notational convenience, I'm going to drop this quaternion stuff, and I'm just going to write this as a pure scalar, minus 2 times n hat dot v. So I've cleaned up the board a little bit here. There's my vector analysis reflection equation, and here's that new quaternion equation that we just derived. nv plus vn is equal to minus 2 times v dot n. And now what I'm going to do is I'm going to write this as a quaternion equation instead of a vector equation. So instead of the vector v prime, I'm going to write the quaternion v prime is equal to, instead of the vector v, I'm going to write the quaternion v. And now notice I have that minus 2 v dot n, which is precisely this quaternion here. So I have plus nv plus vn, which remember that's all scalar. And then finally I have n hat, which is just the quaternion n. Now what I'm going to do is just distribute that n to that sum there. So what I have is v prime is equal to v plus nv, and then I have that n multiplying on the right. Then finally I have plus vn squared. So that's pretty nice so far. Now, I claim that this quantity n squared is actually something pretty special. Let's return to the definition of n. That was just 0 in the scalar part and n hat in the vector part. And now I'm going to just square n. I'm going to multiply n times n, which is 0 n hat times 0 n hat. And upon multiplying, my new scalar part is going to be 0 times 0 minus n dot n. So I just have minus n dot n in the new scalar part. And the new vector part is going to be 0 times n plus 0 times n plus n cross n. So I just have n cross n. And what is minus n dot n? Now remember, n hat was chosen to be of length 1. So this is actually going to be equal to the minus squared length of n hat. And then what is n cross n? Well, a vector crossed with itself is just a 0 vector, so the vector part goes to 0. And like I said, the length of n hat was just 1, so the scalar part is just actually minus 1, and the vector part is 0. So that means that this quantity n squared is a scalar minus 1. So that's pretty interesting that that quantity n squared is all scalar, no vector. So let me make that substitution right here into n squared. So what we're going to find is that v prime is equal to v plus nvn. Then I have plus vn squared, but n squared is minus 1, so I actually have minus v. And lo and behold, those v's cancel, and what I'm left with is that v prime is equal to nvn. So hopefully you can see that's a pretty interesting, nice, compact formula for doing reflections. And just to take a step back, thinking computationally, I have some vector called v that I want to reflect, and I have some plane which has a normal vector called n. What I do is I load all of those vectors into quaternions. I take that quaternion v and I multiply on both left and right by the quaternion n to generate the output reflected vector v prime. Really the quaternion v prime, and then you translate that back to a vector v prime. To convince you that this formula actually makes some sense, let's try to do some calculations. And let's do the same calculations we did before. Let's have that vector v be 1, 1, 1. So 1 in the x, 1 in the y, and then up 1 in the z direction. So there's my vector v. Now I could write that as 1, 1, 1, but since we're dealing with quaternions, we're going to write the quaternion version, which is I plus j plus k. Again, this is the usual physics notation. I represents the x direction, j is the y, and k is the z direction. And then we're going to try reflecting through the xy plane as we did before. Remember that normal vector was 0, 0, 1. It was either 0, 0, 1 or 0, 0, minus 1. But the quaternion representation is just going to be k for the unit normal in the z direction. So there's n, there's v, and we saw before that v prime should be 1, 1, minus 1. So if this calculation makes any sense, then v prime should be I plus j minus k. So let's try doing this calculation. So v prime is equal to nvn, which is k times I plus j plus k times k. And by the way, this product here is sometimes called the sandwich product because the input vector, the input quaternion I should say, gets sandwiched in between these two ends. Nonetheless, let's distribute here. So I'm going to distribute the k on the left, so I have ki plus kj plus k squared. And I still have a k on the right there. So ki is equal to j plus kj, that's equal to minus I, and plus k squared is equal to minus 1. And I still have the k on the right, so I distribute on the right. So I'm going to have j times k minus I times k minus k. Now jk is equal to I. Ik is equal to minus j, but I have the extra minus there, so it's going to actually be plus j. Then I have minus k. And indeed, that is the correct quaternion that I should be getting out for reflecting v through the xy plane. Now here, it's even more obvious that it didn't matter whether we chose n to be plus k or minus k, because we return up here to the formula. If I had minus k instead of k there, and also another minus k there, you get two minus signs and they cancel, so it doesn't matter which n you choose. This formula also has some other interesting properties. Now, if we take some arbitrary plane here, and I consider the unit normal vector sticking out of it, n in quaternion form or n hat in vector form, I claim that if your vector that you want to reflect is parallel to n, then the quaternion product nv is equal to vn. So what that means is that I could just swap around v and n there. So what that implies is that v prime is equal to n squared times v. And what was n squared? That was minus 1. So I get minus v on the right-hand side. And that makes sense, right? Because if v is in the same direction as n, then reflecting it through the plane is the same thing as taking the negative of that vector. And correspondingly, if I take the other special case where v is perpendicular to n, that's to say the vector is right on that plane, then I claim the corresponding quaternion commuting relation is that nv is equal to minus vn. And by the way, I encourage you to prove these on your own. I'm just asserting them here. I haven't shown them to you yet. And now instead of getting a v squared is equal to n squared v, I get that extra minus sign. So I get minus n squared v. So I get minus minus v, which is equal to v, which means that reflection doesn't do anything to a vector that's on that plane. In preparation for the next video, I have a challenge problem for you, which is to investigate the problem of the composition of two reflections. So you're going to do one reflection on a vector, take the output, and then reflect it through another mirror. To draw it out, I have some mirror M1, I have a second mirror M2, which are separated by some angle of theta. I have some starting vector. Let's draw that starting vector in right there, v. I first reflect it through M1 to generate some vector, which will land over there. And then I reflect it through M2 to generate the final vector. Now, it turns out that this composition of two reflections can be done all in one transformation. And my question for you is, what is that transformation? Describe it to me. To help you out here, using that quaternion reflection formula, we start with some vector v. It gets multiplied on both sides by the quaternions n1, and these n1s are going to be the normal vector for the mirror m1. This generates a new quaternion slash vector, and that gets hit on both sides by an n2. That gives the final vector right there. So this whole thing is really a transformation all in one step. So describe what that transformation is. And to do that, you're going to need to do these calculations here. You're going to want to calculate what n2 times n1 is, and also what n1 times n2 is. And that'll do it for this video. If you enjoyed this video, I encourage you to subscribe to my channel. Feel free to like the video if you actually liked it. Leave some comments, including suggestions for future videos. And I thank you for watching.